All right, welcome. So in this video, I want to introduce the Minimax game tree search algorithm that's used to solve two-player games like chess, tic-tac-toe, checkers, and Go. So the Minimax game tree search algorithm, also known as adversarial search, was developed by a handful of different researchers, all of whom were really important contributors to computing and AI. Names like Alan Turing, John von Neumann, really important, first researchers in computing, but also contributors to starting the field of AI. Claude Shannon, who is one of the creators of information theory, and then Herbert Simon, and then who's depicted here, John McCarthy, are two early AI researchers from the 50s and 60s who created some of the first AI labs at universities. So the Minimax algorithm is called Minimax partly because it considers two players, min and max, that are trying to competitively minimize and maximize the score. So the games can often be considered very similar to some of the models we were considering in our reinforcement learning videos just a few videos ago. So I present here just a simple environment that we had in our reinforcement learning world. I've changed it slightly. I'm not going to punish our robot for going into the neutral squares. There's only going to be a reward for going into the pot of gold of 100 and a penalty, if you will, of falling into the pit of spikes of minus 100. But let's imagine, instead of trying to train a robot to avoid the pit of spikes and find the gold, which is what we were doing in our previous videos, let's assume that this robot is controlled by two players, one called min and one called max, and they take turns making moves. And one of them wants the robot to get to the pot of gold. That's the max player, the one that wins if they maximize the score. And the other one wants to go to the pit of spikes. They win if they get the minimum score. And we can imagine this sort of going back and forth. If the min player gets to go first, and we're starting in this position, they'll just jump in the pit of spikes. So let's just imagine for a second that the max player is going first. Then we might see, okay, the max player might move us to the left, the min player might try and get us next to that pit of spikes, but the max player sees, I don't want to fall in there, so they moves them close to the pot of gold, and we might get caught in sort of a back and forth. This doesn't seem like a very fun game, but you can imagine how the game would work. That's the idea behind the Minimax algorithm, is that we have two players. They're playing the game, they're controlling the state of the game, they get to change the state of the game as a result of their moves. And then their goal is to try and manipulate that game down some path to arrive at a goal state that is favorable to them and avoid the goal states that are favorable to the opponent. So that's how we kind of model the game. So as I've mentioned, that means that the game, we're modeling it as sort of a state space, just like we were looking at in the reinforcement learning, as our robot is existing in a state space. Okay, a state space just being a collection of states. Not just sort of thrown together in a bag, but put together with their structure. And that means there are things like initial states. There are things also labeled as terminal states. And then there's also, lying on top of this, a transition function that tells you how to move from one state to another, or what the outcomes of any player's action is going to have on the state when they make that action or play that move in the game. And then finally, we have to have some kind of utility function or some way of identifying the terminal states, the end of the game, and also identifying who has won or has lost in that state at the end of the game. So these are all things that were already built into the state spaces we were looking at in the reinforcement learning world. So I'm just bringing those definitions over with us. And if you aren't familiar with them, please take a look back at some of those earlier videos where I discuss state spaces in more detail. If not, they're pretty intuitive, so we can continue here, and we can recognize that for instance, for the game of tic-tac-toe, we might start our game tree search out at the initial state. So at the beginning of the game, we start with the empty board. That's the initial state. We don't always have to start our game tree search here. Usually, if the game is in progress and we're trying to make a move, maybe our opponent just made a move and now we're trying to pick our move, we will often start a game tree search again, but then we will start from that state because we're trying to figure out what the best move is for that state. But starting our game tree search out from the initial state is basically saying, where is the best place for me as the first player to place my piece, in this case an X? Where should I place the X that is most likely going to result in me winning? Okay, that's most likely going to result in me winning. So that's that first tree. So we're going to do the search. So what does a search involve? So it's called a game tree. So we're going to build a game tree, and we're going to build the game tree by considering what moves we have available. So on the next move, we're going to consider all possible moves that the X player can make. So we'll consider moving in each of the 9 squares that they can make. So in this case, we're considering the X player, since they are the first player. We usually call the first player the max player. And that's just by convention. There's nothing important about the first player that makes them the max player. We just usually make the first one the max player and the second one the min player. And then we assign our utilities based on that. So if X wins, we'll say that they get the utility of +1 because they're trying to maximize. And if O wins, we'll say that they get the utility of -1. And on the next level, we're going to consider every move by O relative to the move that was already made by X. So there were 9 possible moves by X on the last one. Each of those is going to result in 8 other possible moves by O. So the total there is going to be 72 possible outcomes on the second row. Okay, now we can see that this is getting big really fast. Luckily, Tic-Tac-Toe, there's only going to be a possible 9 moves, so we're only going to go about 9 levels deep. If we had to go too much deeper than that, things are going to get pretty out of hand. The other thing that's in our favor, at least, is we're reducing the fan out at each level. So the first fan out was 9, then it was 8, then it's going to be 7, and so on. Every time we occupy one of those spaces, it means one less space for our opponent to move in the next step. So we can imagine continuing. This tree would get really large. This tree, if we drew it, an estimate of how large it might be would be 9 factorial, 9 times 8 times 7 as we go down. However, some of those states, like some of the ones that I've depicted here, are going to terminate early. So I've got 3 terminal states indicated here as well as their utilities. So the first one here is one of the most common outcomes is a draw. So neither X nor O has won. The outcome or utility that I'm going to assign to that in this model is going to be 0. This is a case where O has won. I'm going to say O is the blue player, so I've outlined it here with blue, and I've given it a utility of -1 because we're treating O as the minimizer. X is the maximizer, so this outcome where X has won, and I'll say X is the red player, we will assign the utility of 1. So all of these states, we will call them terminal states, or also sometimes known as final states, and it is common that only the terminal states are the ones that are going to have a utility assigned to them by the game. It's common, but not always. That's because most of the goals of these types of games that have been designed for humans to play is to win, and there is some state at the end that you need to get into to achieve a winning state. Some of the more modern games involve things like scores, and scores may start adding states to some of the interior states where you haven't won or lost yet, but you've still gained some kind of reward as a result of it, and maybe those rewards added together contribute to your winning at the end. Those are things we might be able to consider in playing our game, but it is very common for utility to only be defined on these terminal states, as it is in tic-tac-toe and chess and checkers and even Go. So I mentioned this already, that if we expanded this game tree and we wanted to estimate its size, it might be about 9 factorial. If we compute that, that's 362,880 states. From a computer standpoint, not very bad, actually really easy. If you had to build all of those states and investigate them all to decide on your move, you could do that very rapidly. And that's one reason why, if you're employing if you're playing Minimax for tic-tac-toe, you probably aren't going to be much more clever than just expanding the game tree in the naive way, because it's not large enough that you need to be more clever than that. However, we can note that there's a lot of repetition in these states. For instance, if you get down to the third level here and you maybe have XOX on the top row there, there's at least two different paths that could lead you to XOX. Did I make my X in the left-hand corner or the right-hand corner? There's more than one way that we could get there. And because of that, there's overlap. There are cleverer ways to do this search than to just expand the tree completely, in which case you might arise at fewer states. I mentioned in my last video that for tic-tac-toe, the Nash equilibrium, meaning the optimal strategy for both players, results in a draw, which is why tic-tac-toe is not a very interesting game to play. But when we're only considering the optimal moves by both players, the number of states that you might arise in is actually much fewer. And in fact, the author and the artist, Randall Munroe, who is the author of the comic XKCD, if you haven't checked it out, it's a pretty cool information and computing based webcomic. In this particular webcomic, what he's gone and done is he's depicted the optimal tic-tac-toe moves depending on who you are, whether you're playing X or you're playing O. And the way you use this is you look at the board and you look for the largest red symbol. If you're playing X, the largest red X. In this case, it says top left corner. So what this is saying is if you're X, and you're faced with making a first move, you should make it in the top left corner. Then if you're O, what you do is you look at the corner where your opponent made the move. So we'll look at this top one here because that's where our opponent made. And you can see in this one, it has an X in the top left. And then we look for the big red O. That says if our opponent moved in the top left, we should move in the middle. Okay, then we can go back to the X side and say, all right, I moved in my X spot, but my opponent moved in the middle. So I'll look in the middle square to find what I should do next. And it says, oh, I should move on the opposite X. And we can continue doing this. So following it around, we said X, O, X, O, X. Okay, where should we move? We should move in at the bottom. Okay, I don't want to keep doing this because it keeps getting smaller and smaller and smaller. But no matter what move your opponent makes, you can always look up what you should do to counter them or maybe even win. You can see some of these states, like this one here, results in O winning. So it's telling you your optimal moves. So what's interesting about this depiction is we can see at least visually that the number of states that you actually have to consider to win or play optimally in tic-tac-toe is actually very few, especially on the X side. The O side's only seems a lot worse because it had to consider all possible moves for X to consider. But in this one, if X just moves in the corner as its first move, it's kind of got a very limited structure that it has to worry about. And this is what makes the game really easy to solve and why human children are capable of solving it. So the Minimax algorithm, we just sort of saw a depiction of that. But what the Minimax algorithm actually is going to do is do a recursive exploration of this tree. So we don't actually build this tree in memory as a data structure as you might consider building, you know, a binary search tree. Okay, we're not going to actually have nodes that have links that are connected. We're going to traverse it by constructing the state and then maybe leaving that state, well, probably on a recursive stack for when we come back to it. We're not going to actually connect it up in any way. We're just going to play the game. We're going to make a move, and that move is going to arrive us at a new state. And we're just going to play the game down until we arrive at some terminal state. We're going to register what that is, and then we're going to let recursion let us backtrack back up, again, popping off that stack, maybe finding a state where we need to pursue another branch and then explore that branch. So the type of search that Minimax employs is a depth first search. So we're going to go as deep as we can down a branch until we arrive at a terminal state, and then we're going to come back up, and then we're going to go down another branch and so on. And we're going to do that to effectively simulate playing every single game, or every single game from the current position of the game board, whatever that might be. And maybe it's makes sense that if you can play every single game from where you're at, and figure out what the outcomes are, you should be able to pick out which is the best next move. So which move leads to the most wins or is most likely going to lead to me winning. So that's the strategy behind the Minimax algorithm. So let's actually look at the structure of the recursive Minimax algorithm. Okay, so this is, if you've had a chance to look at my series on algorithms, then this looks very similar to what I call a self-reduction. This is a self-reduction, meaning it's a way to show how the Minimax value or the output of the Minimax algorithm for a particular state is related to the output for other states that are deeper down in the tree. So to get started, I'm going to just mention that what's going to happen in the Minimax algorithm is we are going to return back the value of states. And we, as the maximizer player or the minimizer player, want to achieve either the maximum state or the minimum state. And so when we're considering different game states, if we're in the maximizer's role, we're going to try and pick the maximum state. And if we're in the minimizer's role, it's their turn to play, we're going to try and pick the minimum valued state. And so that's expressed here by these two recursive lines in our self-reduction. The first one saying, if my player at state S is the max player, then I'm going to maximize over all the actions from state S. So whatever actions are available to us at state X, we're going to maximize over them. We're going to try each of those actions, and we're going to plug into the the transition function. We're going to say, if I take this action, what? So that will give us the resultant state. And then this is a recursive call. We're going to recursively go down and say, what is the state of each of the resultant states for all my actions? So maybe I have 4 actions available. Let's call them up, down, left, and right. And I'm going to iterate over them, up, down, left, and right. I'm going to see what is the state I arrive in if I move up, what is the state I'm going to arrive in if I move down, etc. I'm going to recursively ask those states, what are your values? So that's where the recursion comes in. But again, let's just assume we're on one level of recursion. So assume that those recursive calls return back and return us the values. So now we know the value of those 4 possible states. And because I'm a maximizer, I want to have the maximum outcome, I'm just going to pick the action that leads to the maximum state. So I maximize over those actions. And then I'm going to return back, I'm not going to tell you what action that is, I'm going to return back what the value is. What is this going to return me? Am I going to win as a result of this move? Am I going to lose as a result of this move? Or am I going to draw as a result of this move? I will return that back up to the level above me. Now the level above me is a minimizer. So they use this level. They do the exact same thing. If the player at the current state is a minimizer, then we're going to consider all the actions available to the minimizer at that state. And we're going to go through and find the resultant state, one of them which might have been that max one we were just considering. And we're going to see what all those values are. And we're going to pick the minimum of those values because we want to achieve the minimum score. So if one of those states was, for the maximizer was like, this is really good, I'm going to win, well, the minimizer is probably going to avoid that action. If that action leads to my opponent winning, they want to maximize the score, I'm minimizing the score. I'm going to pick a different action that at least leads to my draw maybe, or maybe to me winning, which is my goal. That's where the adversarial nature comes in. So as we recurse down that tree, we're going to keep switching from a maximizer state to a minimizer state, and we're going to just apply opposite roles when we consider all of our children. We just look at all our children and we pick the max, or we look at all our children and we pick the min. Now, as you recurse down, you're eventually going to arrive at a state that's not another minimizer or maximizer node. You're going to arrive at a final state or a terminal state. When you do, we just return back the utility function. So if we return down, if we recurse all the way down and we arrive at a state that is a win for the maximizer, then maybe the utility there would be 1, and we return that utility back up to whoever called us. Maybe it's you can arrive at that state either from a maximizer's move or a minimizer's move. So maybe it's the maximizer, in which case they might say, yes, I want to achieve that state. If it's the minimizer, they might say, no, I want to avoid that state. But when you arrive at that utility, or when you arrive at that final state, we just compute the utility and we pass that back up. Most of these definitions I didn't sort of highlight, but all of these are kind of explanatory. These are just the different components that we borrowed from our state space definition earlier on. So again, if you're unfamiliar with some of these, the delta and so on, I talked more about those in an earlier video on reinforcement learning. So one thing about this particular statement of the algorithm is that it does assume that you can arrive at the final state. So meaning you can search the tree all the way down to the end of the game. This is infeasible in most game trees. Okay, in Tic-Tac-Toe, fine. As I mentioned earlier, 362,000, we can do that. We can go all the way to the bottom from the beginning. But chess or checkers even, you're not going to be able to go all the way to the end of the game for all possible games. That's just going to take way too much time, at least with modern computing. In the future, who knows? Maybe they'll be able to search the whole game tree of checkers and maybe even chess in a matter of seconds, in which case, awesome. But in the meantime, think about John McCarthy and those early AI researchers who had very limited memory, very little, and very slow machines. You had to cut off somewhere. You had to stop your search at some point and then do something else. So you couldn't rely on the utility function in that case. So before we get to considering that, let's take a look at a quick example of computing the Minimax function for a very simple game. Usually our examples for these when we want to show the Minimax algorithm, because even Tic-Tac-Toe, in its simplicity, it's still got 362,000 states in the game state. I don't really want to show that whole game and explore it. That will take way too long. We usually come up with really simple examples. A very simple example is called a two-ply game. That's a game where there's only 2 moves. There's a move for the maximizer, and then there's a move for the minimizer, and then we determine the outcome of the state. In this two-ply game, I'm going to consider the game rock, paper, scissors. But I'm going to consider it slightly different than it is normally played. It is normally played as a game that is played consecutively. We don't have one player go and then another, and the reason is about to become very apparent. But in the types of games that we usually apply Minimax to are games where we do have one player go before the other. So I'm going to consider a case where the maximizer has to play rock, paper, or scissors first, and then the minimizer gets to play rock, paper, scissors second. You probably can already anticipate what the outcome is going to be, but let's see what's going to happen. So when we explore this algorithm, so let's say we're taking the role of the maximizer and we're trying to determine what is our best move. Should we play rock, paper, or scissors? So the first thing we do is we explore our rock branch, and we're doing depth first search, so I'm going to assume we go all the way down and we assume we played rock and our opponent played rock. Rock is a draw. So the utility that I've assigned to this final state is 0. So at this point, the 0 gets returned back up to the minimizer, and the minimizer, often we consider the minimizer keeping track of its minimum as it's going. So at this point it might think, okay, the best outcome for me is 0. As we keep going, we're going to consider other choices for the minimizer now. They chose rock. What happens if they choose paper? Well, if they choose paper, paper beats rock. So this is a case where the minimizer will win by playing paper. So I'm assigning the utility of -1 because the minimizer won. So it's -1. That's the win state for the minimizer. And this will update our best choice for the minimizer. Now I can win if I play paper. And then we can consider our other possible case, which is scissors. If I play scissors as the minimizer, I lose to the rock. That means the rock wins. That's the maximizer's win. So I'm going to give that utility of 1. And because the node above here is a minimizer node, that's why it's pointing down, it's going to pick the minimum. It's not, so this one isn't better for it, this is worse for it, so it's not going to update its state. The Minimax algorithm is going to pass that -1 now back up to the top level. And the maximizer, keeping track, is saying, well, if I play rock, I lose. So let's consider other moves. Let's consider paper. So if I play paper and my opponent plays rock, then I win. Paper beats rock. So that's a 1 state for the maximizer. But the minimizer is not going to, well, I mean, it doesn't know this yet, but this is not a good state for the minimizer. It's the best state it's found, but it's not a good one yet. So we go to the next one and we pick paper. Paper is a draw. And for the minimizer, that's a better state. So the minimizer updates and says, good to go. I like this one better. But we still have 1 to go, so we'll investigate scissors. Scissors beats paper, and that gives us the utility of -1. And again, that's better for our minimizer, so we update the minimizer state. We pass that new -1 up to the maximizer, and the maximizer says, well, that's already what I had. I lost if I played rock, and I've lost now if I play paper as well. So I have one more move that I can consider. I'll play scissors. So I'll play scissors. And the minimizer might play rock. In that case, rock beats scissors. So again, -1, the minimizer wins. And the next case is a case where the maximizer would win. But again, the minimizer is picking this move. And so the minimizer would not pick paper. And same thing with scissors. Scissors would result in a draw. But for the minimizer, the best move is to play rock. So the outcome that we come to as a result of exploring the Minimax tree, we can see that all 3 of the possible moves that the maximizer can make, rock, paper, or scissor, results in a state where the opponent can win. And so since the opponent can pick to win in either of those 3 options, when the maximizer tries to maximize, it's still -1. Meaning, of course, don't play turn-based rock, paper, scissors with someone, because, or if you do, rather, be the second player. Don't be the first player, because you're always going to win if you're the second player, and you're always going to lose if you're the first player. This is another example of a solved game. We just solved this game. We figured out what the optimal move is for both players. The optimal move for the maximizer is whatever you want, because you're always going to lose. And the optimal move for the minimizer is strategic. Pick your move based on whatever it is that the maximizer moved. Now, really the optimal move for the maximizer in such a scenario is don't play this game. This game is not good for you. And that's also a property of solved games sometimes, is when you've got a solved game, the outcome is, well, I'm not going to play that game. Either because you're guaranteed to lose like this, or the game is just not interesting if you're guaranteed to, or if you know what the outcome is going to be at the end. All right, let's go to a slightly more complicated game, which is Tic-Tac-Toe, over our very simple 2-ply rock, paper, scissors. This actually is considerably more complex. But let's not start at the beginning. Let's imagine we're in the position we're X, and we've arrived at this state of the game board, and we need to select our next state. So we can again employ the Minimax algorithm. So what we can do is investigate each of our next state. Here I've sort of advanced us recursively. We're going to try one move for X. We're just going to pick it at random. We're going to try all of them, so we're just going to go through them in order. So I pick the first available move for X, and then I pick the first available move for O as a response to that move by X, and then there's a force move for X. There's only one space left. So considering this path, this is one possible game that could arise from our current state, and it's going to result in a draw. So I'm going to signify that here with this gray box. So this results in a draw, and our I've sort of advanced this a little bit here, but the terminal state will say I'm a draw, and it's going to pass it back up to this state. This state was a move for X, and so this state is a maximizer node. It only had one state beneath it. It had no choice. It had to pick a draw. That's why I just quickly updated it to draw as well. There's no choice here. There's nothing to maximize over. But this state above us This is going to be the state, the move for O, and so it is a minimizing state. And it is going to have two different outcomes that it might have, but at the moment, its best outcome is still this draw. Now, if we consider the other case here, which is going to be a win for X, so if we go down this other branch, O moves here, but then X is allowed to move here and win. This state here is a minimizer branch, so it's going to select the best move for O, which is the left move, which it will result in a draw, not the right move, which will result in a loss. So if we were at O's position and we were here, we now have all the information to pick the left move. But remember, we're in X's position, we're up here. So up here, what we're seeing is if I, as the X player, plays in this position, the best I should expect is a draw, because the minimizer, if the minimizer is being optimal, will pick this move and then result me in a draw, not allow me to get this win. So as the maximizer, even though I'm looking down there and I see a win, I don't count that win as good for me, because I know the minimizer would not pick that move if they're playing optimally. All right, let's consider our next move. So we considered this one. The next one is to put our X here. This state is actually an immediate win. We win right away. Now, if you weren't just a computer kind of blindly exploring states right now, you might be like, okay, I found my move. I don't need to look for any more moves. But in a blind Minimax game tree search, we won't necessarily do that yet. Okay, there are variants that will stop now and move on and move to more other considerations if there are some. But in our naive Minimax game tree evaluation, that's not true. We're going to keep going. But if our node above is keeping track, it will say, aha, I found a winner. So far, so good. So let's investigate the last branch, though. So the last branch here is to place our X in the bottom position. If we do that, one possible outcome is for O to respond by playing here on the right, allowing us to win, or allowing X to win if they move in that bottom left. So that outcome is a win. Now, if the minimizer is keeping track here, it's gonna it might say, okay, the best outcome here is a win. But in our next outcome, we see indeed that there is indeed a draw available. And again, remember, this is a minimizer node, so it's going to pick the best available for the O player, which is a draw, and returning that back up. So our node up at the top, our initial node, is now going to be a maximizer node. It's going to say, which one should we pick? Well, we'll pick the winning move. So it knows that it can win by playing the second move. And this also brings us to a observation that I didn't necessarily make yet, which is the purpose of this computation. You'll notice it's just returning back values. It's just returning back a -1, a +1, or a 0, saying we can win from this, we can lose from this, or we can draw from this move. When we get to this point and we actually have to select our move, how do we know which move it is? Well, all we've really calculated is that we can win. Well, now what do we? Now we go look at each action and we say, well, which one was it that resulted in that win? So in one case, we're doing the max. We're calling the max of these three values. But in the second case, when we're trying to figure out which move to make, we're calling argmax, meaning which move is it that leads to the max. Okay, so that's something that I kind of didn't mention explicitly, and I wanted to point out that at that top level, when it's your turn to actually make a move, you need to do something with that information more than just calculate what the maximum is. You need to figure out which move achieves that maximum. All right, so I did mention earlier that when the game tree gets too large, as it is in most games that you want to play, you're going to have to introduce something new, which is an evaluation function, which is our utility function is very explicit. It's usually only defined on the terminal states, and it just tells us who won or who lost. So our utility function we can think of it as maybe being based on a win condition. Whereas our evaluation function is a little bit more loosey-goosey. It's going to be applied to any state. We should be able to apply it to any state, and it should return back to us some estimate of what that state's value is going to be. So that's the goal of our evaluation function. Now, once we have that, we're going to be able to stop our search at a particular depth. So in our earlier version, we stopped when we got to a terminal state. Well, now what we're going to do is we're going to pass in an extra argument, the depth, and we're just going to recurse down with it. So maybe we want to go 7 layers deep. So we pass in the depth of 7 and we go down. Each time we reduce it, and once it gets to 0, instead of considering moves from that state forward, even though there potentially are, we will apply the value function, our evaluation function, to the state and use that as our estimate of its value. Okay, so this is more commonly what's done in checkers or in chess or in Go. We do a game tree search, but we have to cut it off at some point, and we cut it off at some point and apply some function, which is an evaluation function. So evaluation functions, I mentioned, they are going to take the state of the game as input, and their goal is to calculate an estimate. And normally what that means is a numerical estimate. There's some number that we want to assign, like this is 12 good or -7 or something like that. So it's going to be reducing usually a highly dimension space and reducing it down to a single dimension. So it's obviously going to be a little bit lossy. It's important when we do this to build in specific knowledge about the game. So I use chess as an example because chess kind of famously has some of these evaluations built in already prior to having computers, just for humans to try and evaluate what the value of the state is. And that is that each of the pieces in chess is assigned a point value. So I've got the point values here. So pawns are considered 1 point. Knights and bishops are equally valued at 3 points. The rooks, considered slightly more powerful, are valued at 5 points. And then the queen, considered to be the most powerful piece on the board, is worth 9 points. And then the king, which is the most important piece on the board, is kind of worth infinity points. So if you if you lose it, you lose. And otherwise, every game state is going to have both kings available. So we kind of just ignore the king as a result. We say, okay, the king's going to be there, but to evaluate a game state, at least loosey-goosey, we can just add up how many points each team has, and whoever has the most points is probably winning. Now, this is a hard and fast evaluation function that humans can do on the fly when they're playing the game. But if you're a computer, you probably are going to have a more sophisticated one than this. So not only would you maybe consider what pieces are on the board, but you should also probably consider where they are on the board. And you can come up with a very elaborate evaluation function if you start doing that. Now, it's one thing to recognize is that what we're describing here are what we commonly call heuristics. Heuristics meaning that they're not a hard and fast algorithm that's computing some specific function. They're estimates, they're approximates, and we also have ulterior goals or ulterior motives with them. For instance, we want them to be quickly computed because we compute them often. When we're searching this game tree, every move, we go down and we see all kinds of these states, and every time we see one, we have to call the evaluation function on it, so we want it to be fast. So very elaborate ones that do lots of analysis of the position of the board that take lots of time, that's probably not very valuable. One thing that's become more common in modern days is maybe we replace this function with a neural net, something that we can train with a neural net so that it can be quickly computed, but it might also be able to take in a lot of complex information from the game state. So that's sort of a more advanced way to modify this Minimax algorithm. Another important thing to recognize when doing a depth-limited search and cutting off our search at some point is that sometimes you end up cutting off in the middle of a very important sequence of moves. So again, I'm going to use chess as an example, but this also occurs in checkers and in Go, where maybe one move is maybe an important threatening move that kind of forces a sequence of 5 or 6 moves to happen. So in chess, this happens a lot when a piece gets taken. Maybe I take your piece, then you respond by taking my piece back. And sometimes those exchanges go on for a while. Maybe 2, 3, 4, 5 pieces get exchanged. And often the value of that exchange is not known until the end, because at the end, if it's been equal points to equal points, I lost my bishop and you lost your knight, then it turns out that that's a fair trade. But if we stop our search in the middle of that trade, so I've taken your bishop, but you've not yet taken my knight, and then I run my evaluation function, it might say, great move, this is an awesome move, we should make it, okay? When really it's not, it's a neutral move. Or worse, it's a bad move. Maybe what I've done is I've taken your bishop with my queen, and I stopped it before I realized on the next move my queen is going to be taken by your pawn or something like that, which would be a bad trade for me. And because I've stopped my search early, I go and make the wrong move and end up losing my queen. So this is something that was observed when making game tree searches. Oh, sometimes they make these dumb moves. Why? Oh, because they cut off their search at the wrong point. So as a result, our goal is to try and cut off at not those points, at after the exchange. So what these are sometimes labeled as is, we call them a quiescent state, a state where the position is settled, where the exchange is over, or before the exchange has begun. Both of those are quiescent states, but once the exchange begins, we are in an unquiescent state and we should not stop our search. We should continue searching until we arrive at another quiescent state. Now, how do you determine if a state is quiescent or not? You need to have some kind of evaluator that tells you that. So that's another function that tells you, hey, is this a quiescent state or not? So that's adding another layer of complexity on there, but it can avoid you from these unlucky places where you're going to cut off your search and unfortunately maybe make the wrong move. All right, so this video was about the Minimax game tree search. I hinted a little bit earlier about how sometimes we cut off branches when we've already found a real good move or a real bad move. We know that we don't need to search any other branches. This is a strategy called alpha beta pruning, and that's something that I want to look at in my next video. So I want to thank you for watching this video, and we'll see you in that next video.